his work on the quantum cryptography. Herewith, actually, I invite Professor Pathak to deliver his talk.
Thank you, Raj. And before I start, I would like to thank Professor Panigrahi and all the other organizers for organizing this event regularly and connecting us to so many students. And some of my present PhD students also came from this meeting. It's the first meeting when we meet physically, and some of them continued the interest and lately joined us for PhD program. So I just first share my screen and then
yeah.
So is it visible properly now?
Yeah, it's visible. Just play 1-2 slides so that it's moving or not. Yeah, it's moving. Perfect.
So this means I mostly work on quantum cryptography, but when the organizers shared with me the schedule, it was a particular week for quantum optics. So I thought that I'll restrict myself to quantum optics. So and I choose an interesting topic called quantum optics in the era of quantum information. Now so when I was a PhD student, means we started working on quantum optics, and quantum optics itself was the subject. Then things evolved in such a way that we all moved more towards quantum information, learn new things, new applications, like Ashok was talking about quantum cryptography. So we work mostly on quantum cryptography, but it will be, to be honest, when I was a PhD student, I did not know about quantum cryptography. So that whole community of working on quantum optics gradually moved for quantum information, but quantum information is not the entire thing of quantum optics. So where is the connections? Is there a sense of doing quantum optics even in the era of quantum information? So I thought of talking about those things at the last lecture, but then I inquired about the participants, and Professor Panigrahi told me that there are many undergrads. So before I start, I just want to keep it interactive, and I want to know from the students, do you know what is quantum optics? So this is the last lecture of this set of quantum optics window of the workshop. So can anyone tell me what is quantum optics? You have already heard so many lectures on quantum optics. This is the last lecture. So what is quantum optics? Okay, as no response is coming, I assume that I have to start from scratch. And the first slide shows a couple of pictures. So the top left is E.C.G. Sudarshan. So he is one of the father of quantum optics in the modern sense, the way we visualize quantum optics. And of course, quantum optics contain a lot of debate. And there is a nice article by Simon who describes the events around 1963, which involve E.C.G. Sudarshan, and the right-hand top picture, Roy Glauber. So Glauber got Nobel Prize, and what is showing in the poster is alpha. The state alpha is called coherent state. So it's one of the most important thing, and we'll come back to that. So Glauber and Sudarshan made some kind of framework of modern quantum optics. In the bottom, we show some pictures. So the extreme left is Dirac. So you see, in the origin in quantum mechanics, in the beginning, what are kind of things happen? So first thing come where first got the nature of quantumness. The word quantum means discrete. Was Planck's law. So in Planck's law, it was assumed that the walls of the cavity emits energy in quanta, h nu, 2h nu, 3h nu, etc. But he never told that those are propagating from one place to other place in quantum. So Einstein, while explaining photoelectric effect, tell that. So Einstein's notion of light quanta is a bit different from that of Planck. Planck thought it's just an emission in packet, but he never told that they do propagate in packet. Einstein told that they do propagate in packet. Now, in all the textbook, it is taught that photoelectric effect is something which requires the notion of photon or quantized light. That's not the case. Photoelectric effect can be understood even if we consider that the atom is quantized. So this is the point where history of science is important. Einstein was doing it in 1905, and the notion of quantized energy level come with the Bohr model, which happens in 1913. So Planck's law was in 1900, so Planck's law was already there, but Bohr model was not there when Einstein was working on photoelectric effect. So photoelectric effect has an interesting history, but the point we are trying to draw that first people tried to quantize light, but eventually when these are quantum physics, still there is no dynamics, there is no equation of motion. When Schrodinger equation came, in Schrodinger equation you write h bar square by 2m minus h bar square by 2m. So this m has to be non-zero. If m, rest mass of a particle, is 0, then it will blow up. So this was for massive particle, or for particle, Schrodinger equation was for particle having non-zero rest mass. So it was not for light. So initial applications of Schrodinger equation was for hydrogen atom, helium atom, and harmonic oscillator and such thing. So we had to wait for Dirac to give an equation of field and to quantize field. And after quantization of the field, people realize, and you can realize it pretty easily even if you don't know all those things, that harmonic oscillator as a Hamiltonian of the kind of ax square by 2 plus b x dot square by 2, which is analogous to Poynting vector, which also describes energy for electromagnetic field. So you can more or less describe it in same way, and even if you don't know second quantization, so the sense of second quantization is that first quantization tell me that the quantization which comes from Schrodinger equation, quantization of energy or other properties of the matter, and quantization of the field follows from Dirac, and that's called second quantization. So even if you don't know second quantization, you can understand the analogy of harmonic oscillators, and you know that harmonic oscillators energy also go from half h nu, 3 by 2 h nu, 5 by 2 h nu, and the photon also behaves somewhat like h nu, 2 h nu. So the packet sizes are same. So there is some analogy, means without going in deep mathematics, we are just mentioning that. So this comes from Dirac. Then L. Mandel did most of the initial experiments on quantum optics. And Emil Wolf played a very important role in initial quantum optics. And here is our own hero, Professor Girish Agrawal, who was the inspiration for many of us for doing quantum optics in India. And he has also contributed largely on quantum optics, and he is also one of the speakers in this conference. So with this background, I asked the first question, which I asked you a few minutes back: what is quantum optics? So the subject that deals with optical phenomena, matter-field interaction, that can only be explained by treating light as a stream of photons rather than the electromagnetic wave. So you cannot consider light as, say, solution of Maxwell's equation, which is a wave, and explain a phenomenon if it is quantum optical. So whole thing is matter-field interaction. So you don't speak normally in this term, that matter field interaction, but whatever you do, photoelectric effect, light is coming and falling on a matter. You think of Compton scattering. It is that you have a matter who is giving the free electron, and then the light is interacting with this. If reflection happens, you need light and you need some kind of medium which has a refractive index, change in refractive index. So reflection, refraction, dispersion, whatever you can think of is actually matter field interaction. A light is focused through lens. The lens is matter, and then you have light. So mostly you handle matter field interaction. So in the cartoon, I'm asking this light is telling that after so many years of interaction with matter, I don't understand you. And the matter is saying, for a better understanding, you have to be quantized, as our relationship is quantum optical. So that's the gist of what quantum optics is. So optics can be divided into three parts: classical optics, semi-classical optics, and quantum optics. So classical optics is traditional optics in which everything is classical. So your field is solution of electromagnetic wave, light is solution of Maxwell's equation or electromagnetic wave. Atoms are Hertzian dipoles. So wave optics converts all the geometry, covers all of geometrical optics in essence. Now, semi-classical optics is one in which I can consider the matter or atom is quantized, but light is still solution of Maxwell's equation. So light can be treated as electromagnetic wave. And quantum optics is dealing with those phenomena which cannot be explained unless we consider both atom and light as quantized. So we essentially need the idea of photon. So what is photon? So Einstein never used the word photon. So it was G.N. Lewis who coined the term in 1926 in absolutely different meaning. He called it, he was a chemist, and he called it because it appears to spend only a minute minute fraction of its existence as a carrier of radiant energy. So he had an idea that it is something like a subatomic particle. So but the meaning is changed, and now we all feel that we know what photon is, and in the definition itself, I'm calling that, but the case is different. The last 2 decades or 2.5 decades of life, Einstein tried to find out what is the dimension of photon. And Einstein even made a statement that after 50 years of continuous work, I don't know what photon is, but today every rascal thinks that he knows what photon is. So photon is a pretty interesting thing. So those who have little bit exposure of quantum mechanics, they know that photon does not have a wave function in position space. Why not? Because you know that photon has a fixed momentum h nu by c. So if the momentum is fixed, then the position is absolutely uncertain. And when position is absolutely uncertain, if you associate a wave function x with photon, then mod x square will not have a physical meaning. Mod x square is the meaning that what is the probability of getting it at the position x. So if position is absolutely uncertain because the momentum is certain, then mod x square cannot have a physical meaning. So photon is very interesting thing, and photon is in the core of quantum optics. But you often heard something called photonics. Most of the things we do under photonics does not really require photon. They can be done with the classical light. So first I'll start with what is not part of quantum optics. So all these fiber optics people, they will often say that what they do is photonics. You will find that there are center of photonics, but they don't need photon. For almost all the cases means which fiber optic people are doing, all kind of nonlinear optics they are doing with fiber, it is fine that they consider light as solution of Maxwell's equation. Anyway, so here we show, I already mentioned about photoelectric effect, that which can be understood by semi-classical theory. Here I mentioned about a classical derivation of, I show a paper, a classical derivation of the Compton effect by C.V. Raman. So C.V. Raman, so in every textbook which you come across, it has been told that Compton effect establishes that light is particle, because if you consider light as wave, you cannot explain, but there are ways that you can use semi-classical theory and explain Compton effect. So in the right-hand side, I show an old paper which also discusses the semi-classical theory of Compton and photoelectric effect. So why I am showing this? Because these are the examples which always students give, that where it is established that light has particle nature and then wave-particle duality come. So is there really any phenomenon which cannot be explained under semi-classical theory? So one such thing is lamp shift. So if you have not heard of lamp shift, by Dirac theory, which I mentioned, the energy level 2s half and 2p half should have the same energy, but in reality it is found that there is a gap, and 2s half level is higher than higher in energy with respect to 2p half by 1057 megahertz. So this is the frequency. If you multiply with the Planck constant h, you will get the corresponding energy. So h, this is also used as a unit of energy. So now, how was the lamp shift explained? So here comes something called vacuum fluctuation. So this was explained by considering interaction between vacuum energy fluctuations and hydrogen electron in these orbitals. So more specifically, the effect of the fluctuations in electric and magnetic fields associated with the vacuum. So how to visualize this? Quantum optics is a pretty counterintuitive thing. We are talking about vacuum, and at the same time, I'm talking about associated electric field and magnetic field. So gradually things will be clear but what I'm saying that this is one phenomena which cannot be explained by semi-classical theory. So people come up with another idea. People come up with the idea that let's add this one to explain lamp shift. So we go for we want to understand lamp shift within a picture which is not fully quantum. So what we did, we considered that there is a semi-classical theory. In this theory, I add as a top-up or ad hoc addition vacuum fluctuation. So if vacuum fluctuation is added with the traditional semi-classical theory, then lamp shift can be explained. So this is called toy theory, and this gives a relation with quantum foundation. So quantum foundation, this is something which we do in our group also. We often look at the hierarchical axiomatic structure of quantum mechanics. So quantum mechanics is on certain axioms like collapse on measurement. So Ashok was talking just now that when you are doing BB84 protocol and you have a 45-degree polarized photon and you do a measurement in horizontal vertical basis, then it will randomly collapse into horizontal axis or vertical axis, and so your plus state will collapse to 0 or 1. So just like that. So this is an axiom. So we can think of a theory which has everything classical and only this collapse on measurement. So that will be a toy theory. Then I can add some other features, non-locality. I can add some other features. So you can have an axiomatic character and you can create that. It's not a whole quantum mechanics. You have part of the features of quantum mechanics and make a toy theory. And can they explain lamp shift? The answer is yes. And construction of such toy theory is very common in both quantum optics and quantum information. So I'm still not giving you an example where full quantum picture is needed and where you have no option to agree that there is something quantum optical. So there are different kind of atomic systems. So these are atomic energy levels, C, B, A, and from the allowed transitions, the shape is defined. The left-hand side is called V-type system because if you look at this curly arrows, this makes a shape of V and this makes a shape of lambda. So, and a nice example is called quantum beat. So in this case, the result of self-consistent fully quantized calculation. So I'll not show calculation, that's beyond the scope of this lecture. So we get some kind of additional term. So in this case, the result of a complete calculations differ substantially from those obtained via a semi-classical theory, even when augmented by the notion of vacuum fluctuation. So what was sufficient to explain my lamp shift will not be sufficient to explain the behavior of V-type atomic systems and lambda-type atomic systems. So V-type atoms have a beat term, but lambda types do not. And this is a situation where you have to go for a full quantum picture. So there are simple examples where quantum optics appears, and this is early history of quantum mechanics. So I started from Planck. I mentioned about Einstein. The interference of single quanta was observed by Taylor. Einstein's talk about radiation fluctuations, but in 1927, Dirac actually give quantum theory of radiation. So that was the birth of second quantization. We'll talk about Hanbury-Brown twist. So is an excellent experiment, and we already mentioned about Glauber and Sudarshan in 1963. So things keep on happening, and gradually you see that first photon anti-bunching, violation of Ben's quantity, squeeze light. So theoretical idea was there. Gradually the experiment come in 80s, and you see that this is happening in 1985. Already BB84 protocol of quantum cryptography has come, but separate many things happens. Bose-Einstein condensation was known for long. Experimentally it is observed. Slow light, ultra slow light, and so recent interstellar single photon sources, Bose-Einstein condensations, quantum computing applications, slow light, and of course quantum cryptography. So the question is, in all such things, means how these things are connected. Means how quantum optics is connected to quantum information, what kind of training in quantum optics can be used for quantum information. So we continue, and I mentioned that there was an ugly debate between Glauber and Sudarshan regarding the quantum coherence, means how it was introduced, and so who was first, and there is a nice article by Simon and others. So now debate is an integral part of quantum optics. And to be more honest, debate was always there in optics. So you think about, which you know, that Newton versus Huygens debate, that light is particle or wave. Then we are talking about something else. Debate is, so Glauber-Sudarshan debate is much discussed, but there are other debates too. One of the most important experiment of quantum optics is Hanbury-Brown-Lewis experiment, or it's normally written as HBT, which was published in 1956. And they employed intensity correlation to measure coherence. And ultimately, we just, whatever we want to do, we want to manipulate coherence. The idea was so radical that many people could not accept it, but they could not deny it also. So that actually led to a nice debate, and I'm sharing the link, and you can copy the link and check it. But here I also want to make a interesting comment that Robert Hanbury Brown was born in India. His father was an army officer and posted in South India. And in Nilgiri Hills, Hanbury Brown was born. But from the age of 3, he was educated in England. Anyway, so this is a historic note. So with the advent of quantum information, it becomes less exciting to do quantum optics. Is it so? The answer is not. Actually, when you do quantum information, many things, means like you are doing factorization. You can do factorization in quantum world, you can do factorization in classical world. So all the threat of classical cryptography is because of the possibility of Shor's algorithm. That Shor's algorithm will be able to factorize very fast and break the RSA cryptography code or Diffie-Hellman code. But the question is, why it can do something in quantum world that cannot be done in classical world? So there must be something non-classical. So something, either you have a state which is non-classical, because everything is quantum. Classical physics is a subclass of that. So certain things have classical analogy and certain things do not have classical analogy. So if you want to have some quantum advantage, you need a non-classical state. So what do we need to establish quantum supremacy? Non-classical states. So those must be the states which does not have any classical analog. So if you are employing a state which is a classical analog, then you can do the same task in the classical world also. So either you have to use a non-classical property like Bell's inequality violation, or you have to use a state which does not have a classical analog. So experiment, so you need, in essence, you need non-classicality. So experiment of doing quantum optics, excitement of doing quantum optics is enhanced by experimental observation of laser without inversion, use of squeezed vacuum state in LIGO, electromagnetically induced transparency, absorption-less dispersion, etc. No, the beautiful thing is that in today's world, which is much controlled by machine learning, artificial intelligence, etc., many things can happen which was only in imagination. So far, you talk about email and e-business or e-commerce, but there can be e-murder too. How? Suppose you have a driverless car and I hack the car and ask the car to strike in a pool or just fall down in a river or something. You have an automated lift. I hack the lift and I just ask the lift to drop directly. So e-murder by hacking your driverless class, such things are possible. So how to protect them? Protect from such incidents. So you need unconditionally security. So about the security, previous lecture was focused on. So I'll not go in those applications. Rather, I will claim that such quantum advantage can be obtained if you have a non-classical states, if something which does not have classical analogy. So what would ensure the success of second quantum revolution? So it is often told that we are in the march of second quantum revolution. So then there must be some first quantum revolution. So what was that? So first quantum revolution was when transistor was built, laser was built, because all this needs discrete energy level. Unless there is a discrete energy level, a conduction band, valence band, and in between a forbidden band, you don't have semiconductor. Classically, all energy levels are allowed. So classically, you cannot have a semiconductor, and unless you have semiconductor, you don't have diode, you don't have these computers and such things. Now, laser also require at least 3 levels. We are not talking about such things, such quantum mechanics. We are interested about more weird properties of quantum mechanics, like collapse on measurement, Bell's inequality violations. So when we deploy those properties of quantum mechanics and develop some kind of applications, they will lead to second quantum revolution. So one such example was discussed in the previous talk. So the ability to generate, control, maintain, and manipulate the non-classical states will only, so these are the quantum states having no classical analog. So the states, now, how do you know that the state has the classical analog or not? The tools of traditional quantum optics has received a new meaning with the advent of QIT. So for example, there is something called KLM approach. So this is used for making optical quantum gates. So you want to make a CNOT gate or a similar gate, KLM approach is used. And there is something called quantum state engineering, which quantum optics people used to do traditionally, where we have a couple of linear optics and detectors, and only when certain detectors click, so when the conditional things happens, then we say that this has been succeeded. So the state is engineered, or absolutely similar things happens while you design CNOT gate. So for newcomers, it will be difficult to follow, but for those who are familiar with quantum optics and quantum information, they can easily understand this analogy that KLM approach is exactly what we do for quantum state. Now, I begin with the picture of ECG Sudarshan. That was my first slide's top left picture. So he introduced, and that was the debate which who introduced this. This is now called Glauber-Sudarshan T function. So this is something called quasi-probability, because it can have a negative value and probability cannot have a negative value. So this is quite analogous to probability. And this is something which gives me the idea of whether a state is non-classical or not. So how it happens. So by now, since the school is 4 days old, so I assume that somebody has told you about pure state and mixed system. So in quantum mechanics, you cannot always write things in terms of wave function, and you have the whole thing is called bracket. So if I divide into 2 pieces, the left-hand piece will be called bra, the right-hand piece will be called kate. So this is the symbol. So this is my kate xi, and corresponding for a pure state, rho is kate xi, bra xi. But there is a mixed state. So with certain probability, this is xi I, with certain other xi 1, certain other probability xi 2, certain other probability xi 3. Then I write the mixed state density matrix like this. So rho is equal to summation over I, pi, kate xi I, bra xi. Now, if it becomes continuous, then you know that for continuous, the summation will become integration. And I write, and then I choose a particular basis. The basis is coherent state basis. I'll introduce coherent state a bit later. And you can, if you know annihilation and creation operator, you can note that this is the eigenkate of annihilation operator A. So P alpha, kate alpha, bra alpha, D2 alpha. This is the density matrix, and this is just the continuous variable expansion of the previous period. Now, if a state can be written in this way, and P alpha is shorter than 0, shorter than P alpha shorter than 1. So then you can interpret it something like a probability, as before Pi was probability, and then the state is called classical. If not, if P alpha become negative, say, then it cannot be probability. So if the classical analogy drops, so it's no more like a probability, it's called quasi-probability, and such states are called non-classical. Now, I say something technical and then I'll come back to something more basic. So measures of non-classicality are neither unique nor monotone of each other. So there are many such measures, and one way to measure single mode non-classicality is that you take a beam splitter. One mode is vacuum, and the other mode you give a single mode non-classical state. Then the output will become entangled. So by now you must have heard a lot about entangle. So a 2-mode entangled state is such that you cannot separate what is the state of the first. So it's a non-separable state. So if it is separable, then you can write that, suppose you have two mode A and B, if you can write that xi A tensor product xi B as the state xi AB, then it is called separable. If not, it is called entangled. So if you put in a beam splitter, there are, suppose this is your beam splitter. So one mode is input mode is this, one input mode is this. And one side I am giving vacuum, and so from the bottom I am giving vacuum, from this side I am giving a non-classical state. The output will be entangled. So output will also have two modes. And however, if it is a classical state, then the output will become separable. So now entanglement has many measures. So I choose such a measures like concurrence and negativity and plot it. Now if you choose, suppose you follow my mouse, and I choose a state like around 0.4 and 0.1 and call it A. So this state is more non-classical than the B, which is around x-axis 0.2 and y-axis 0.2. And I can claim that A is more non-classical when I'm using concurrence as a measure, but B is more non-classical when I'm considering negativity as a measure. So if you choose different measures, so nobody knows that there is no unique measure of non-classicality. And it's not only the case, because we are ultimately using entanglement measure. So entanglement measures are not also monotone of each other. And you can see that entanglement is something which become actually popular after quantum information become popular, but this has a clear connections with quantum optics. Now, similar thing observed in quantum coherence. So this is a bit old slide when the papers are published in the later 2018. And so non-classicality, and so these characteristics are same, and we find out those boundary states like and mark them. But main point we want to show is that whether you, just like non-classicality I was measuring through some entanglement potential, here is quantum coherence, and quantum coherence are measured with relative entropy, which is plotted in x-axis, and CL1 norm, which is plotted in L1 norm is plotted in y-axis, and you can see that they are not also monotone of each other. So here it is clear that I have a state A and B marked properly in the first graph, and you cannot decide that which one has more coherence. Now, how do we theoretically investigate the existence of such non-classical features? So there are several such things, and normally we get back to uncertainty relations or moment-based relations. So the first I have listed squeezing, that delta x square shorter than 1/4. So we all know about the uncertainty relation, which tells you that position and momentum in the same direction cannot be measured simultaneously with arbitrary accuracy. So that's a particular case of Heisenberg uncertainty relation. Actual statement is that if you have two operators which do not commute, you cannot measure the corresponding properties simultaneously with arbitrary accuracy. So in case of light, we can introduce something called quadrature. So x is a quadrature, and which is written, x1 is written as half a plus a dagger, and x2 is written as 1/2 a minus a dagger. And most of you know that a comma a dagger is not equal to 0. A comma a dagger is 1. So a is annihilation operator, a dagger is creation operator. So x1 and x2, since they do not commute, they do have an uncertainty relation. And in the uncertainty relation, the product is bounded. Now I can reduce the fluctuations in or uncertainty in one quadrature. So x1 is a quadrature at the cost of fluctuations or uncertainty or noise in the other quadrature. So when it happens, then it is called squeezing. So squeezed in x1, so delta x square shorter than 1/4 is squeezing. So this goes through the noise below the coherent state. And this helps me to do various accurate measurements, which we are doing in the quantum information world and in quantum metrology. And in addition, you all know about the LIGO experiment, which has find out the gravitational wave. So in LIGO experiment, actually what is implemented is a Michelson interferometer. And in Michelson interferometer, you all know that the light falls on a beam splitter and another port of the beam splitter is left vacant. Then we will consider that a vacuum is coming But we want more accuracy. So what we do, we pump in squeezed vacuum state through the other port, or so-called empty port of the Michelson interferometer. So this kind of states are used in LIGO. So there is something called anti-bunching, and here is a criteria. So this is of course higher order anti-bunching. So then there is amplitude pi over anti-bunching. Then there is Duan criteria of entanglement. So you see, if I have AT and A dagger T by some way, we can find out entanglement in the quantum optical systems. We can find out entanglement from the lower two criteria. These are called Hillary-Juveri criteria. So what we do, usually we use something called Shane-Mondel approach to obtain time evolution of the field operator. In the beginning, I mentioned that we study matter-field interaction. So matter-field interaction leads to some kind of Hamiltonian. And then we look at the existence of non-classical states in those physical systems. So what are those physical systems? So here I give some examples from several physical review papers of ours. So the message is more important. The calculation is not that important. You don't need to understand the Hamiltonian, understand the physical system. So here is a nonlinear optical medium chi1, and in the top there is another nonlinear optical medium chi2. So chi1 and chi2 define susceptibility. So this is linear in that sense, chi1, and this is chi2 is nonlinear, and two lights are coming. So these green arrows are showing light, and they're allowed to interact a bit. So this is what? This is a optical coupler, and each of these fiber you can consider as a waveguide, and you can make in the laboratory easily this kind of coupler. And there is something called momentum operator, which is equivalent to this, equivalent to Hamiltonian. And once you write this kind of Hamiltonian, then what you can do, you can apply Heisenberg's equation of motion. You can write H comma A to find out A dot, H comma A to find out A double dot, and then you do a Taylor series expansion. If you do so, then what you get is a called short time approximation method solution. But we have some perturbative techniques which are better than those, and then you finally get AT and A dagger T. And then in the previous thing, you have shown that how will you get delta x square, x1, etc. So you know the operators and time dependent operators you obtain by solving the equation of motions, and then finally you calculate delta x square or any of this quantity, because if I know AT and A dagger T, the time dependence of these operators, I can easily calculate this. But I have to define initial state also. So, and normally we consider the initial state as Coherent state. So all these are showing entanglement, anti-bunching. So EA1, B1 means like N is equal to 1, M is equal to 1. This is showing Hillary-Juveri criteria, and between different modes, we are showing entanglement. Now, I'll show you something more interesting, which you can visualize easily. So look at the picture in the right-hand side top. So here, the red beam is going up, and then, so this is taking up, so this is called pump, and then it can come like B, or it can come like D. So can you recognize this with something? Can you recognize or map it with Raman effect? So this is like pump mode, phonon mode, Stokes, and anti-Stokes mode. So you have 4 modes, and then you can choose. Once you can solve this Hamiltonian, you can look for entanglement in them, this using the criteria. So entanglement is essential requirement of quantum information, but traditional quantum optics tools can tell you that which physical systems will give you useful entanglement. Entanglement is more common in nature, so separability is rare. So most of the physical system you study, you will find out entanglement. But then you have to know the dynamics of entanglement, that how much useful it will be at, or for how much time you will cause interaction, etc. So these are similar calculations for different systems of interest. So in the right-hand side top, I show a system. You see that A dagger square A square plus B dagger square B square. So what kind of things are they showing? So these are actually defining the interaction. So here is a double well kind of system. So B mode are this side and A mode are in this side. So these are both are independent BEC. And if now you can define atom-atom interaction, you can define atom molecule kind of interaction. So if it is atom-atom interaction, means one is destroyed from this side, one will be created in this side. So total number will be conserved, and such physical systems can be easily studied using Shen-Mondel approach and leads to squeezing, entanglement, and many such non-classical properties. So there is another optical system. So these are examples of quantum optical systems. So without calculations that what kind of systems quantum optics people study. So this is a cavity, and cavity is driven by a field. So this is showing the driving field, and one of the mirror is oscillating, and then you can write the physical system and calculate again the annihilation operator, creation operators, their time evolutions. So same studies you can extend to something which is of much interest now is PT symmetric systems of couple cavities. Then we so far talk about non-classicality. Another interest at the moment in quantum optics, is called non-Gaussian. So coherent state is Gaussian, but there can be states which are non-Gaussian. And one simple way to see whether a state is non-Gaussian or not, to plot its Wigner function and check that Wigner function has negative part or not. But that's not the only way to check non-Gaussianity. So a hole in the photon number distribution is a witness of non-classical. So what does it mean? So just like you write a qubit as alpha 0 plus beta 1, you can write an electromagnetic field as C0 Ket0 plus C1 Ket1 plus C2 Ket2 and so on. What does it mean? So it means that in the electromagnetic field, the probability of getting 0 photon, Ket0 corresponding to 0 photon or vacuum state, is modulo C0 square. Probability of getting 1 photon is modulo C1 square and so on. So modulo C0 square is P0, modulo C1 square is P1. So Pn is probability of getting n photon. Now, if it is 0, so that means there is a probability of getting 1 photon, 2 photon, but suppose there is no probability of getting 3 photon is 0. And then again, there is some probability of getting 4 photon, 5 photon. So that at n is equal to 3, I have a hole. So P3 is equal to 0. So that's a measure of non-classical. That's it. So what does it mean? So it means that if you add a photon to the distribution, then you will have a hole at n is equal to 0. Because if you add everything, that now the 0 photon state has become 1 photon state, 1 photon state become 2 photon state. You could not have a minus 1 photon state. So there is no vacuum, and then there is a, so that will be a non-classical state. If you make a finite dimensional state, so engineered quantum states, a finite dimensional state, then it will definitely be non-classical. So these are easier to follow. So every finite state is non-classical. So effect of pattern addition and subtraction on non-Gaussianity inducing operations can include non-classicality. So photon addition will always introduce non-classicality because that will create a hole. So here we plot so we described P, but here I plot some other quasi probability. So this may go a bit above, but what is the purpose? Why I am introducing this non-Gaussian states? Because the lecture was supposed to be on the connection between quantum optics and quantum information. So here I mentioned about another work, continuous variable control quantum dialog using photon added then subtracted coherent state. So far I was talking about quantum optical techniques, engineered quantum state. So this process is like, I have a coherent state. Coherent state is very easy. Output of the laser is coherent state. Now you want to add a single photon and then subtract a photon, or you want to add 3 photon and subtract 2 photon. So these are quantum state engineering. So you had a coherent state and now you are doing engineering and making a tailor-made state out of that. So those engineered quantum states are often used for quantum cryptography, just like continuous variable control quantum dialog. So what is quantum dialog? So What Ashok told you in the last lecture is about quantum cryptography, that in a secure manner, you are communicating between Alice and Bob. Now, what you are doing? You are just creating a key. You are not sending a message. After that key, suppose you have a key 0000100 something, and then you have say 8-bit key and you have a 8-bit message, you will bitwise XOR and send that. So the communication is classical. So people ask that, is there a possibility that direct communication, that without pre-generation of the key, I'll communicate directly? So there are several such protocols, and this is one of our interests to work on, quantum secure direct communication. But that past such protocols were one way, that it can allow me to communicate with Alice. Alice communicates with Bob only. But many times it happens that the communication is both way, that Alice is communicating to Bob and Bob is also communicating to Alice, just like in telephone. So such things are called quantum dialogue, and this shows a protocol of quantum dialogue which uses the quantum optics trick. So quantum optics tricks and quantum informations are highly correlated, and this shows quickly that many facets of those. So I'll skip this part. Now, there is something called master equation. So I'll not go in detail of the master equations. So in a quantum optics workshop, master equation should appear, and master equations helps me to handle open quantum system. So a very lucid introduction to what open quantum system is. So whenever you have been taught quantum optics, so quantum mechanics in your undergraduate classes, I'm assuming I'm addressing mostly to the undergrads who are working in the workshop. So you have been taught about particle in a box. So as if there is nothing in the world apart from particle and the box. But in reality, you have everything else. You, me, the chair, table, everything else is there. And they are produced in the environment, and intentionally or unintentionally, it can interact with the environment and the state may change. So I was telling that on measurement, it collapses, but it can collapse with the interaction with the environment also. So you have to take care of those effects, and those effects are taken as noise, and we often see the effect of noise. So FA is fidelity and eta A is a noise parameter. So as the noise increases, the fidelity decreases. So in different protocols and for different noise, this kind of impacts are checked. And I'm not going in what is BB84 subroutine or GB subroutine, but you all are part of noise. And that's what is explained in this cartoon, that our interviewer is asking that whether you have worked on quantum optics ever, quantum information ever. And the candidate is saying that in all the well-known experiment, I was part of the experiment because I was part of the environment. I show that the fidelity decreases because of noise, and now I am explaining this. So you see here, a man is being teleported. So you will come across quantum information course, and you will talk about, many people will talk about quantum teleportation. So this is something like a teleportation station in New York, and somebody comes to New Delhi, and you see that the nose and ear has been changed. So it's not a real copy of this person. So air hostess says, analogous teleportation hostess is saying that, sorry sir, due to noise in the teleportation, we cannot achieve the unit fidelity. So copy is not one. So that's the biggest problem. That's why we don't have a scalable quantum computer. So noise is the biggest problem. And how it is handled? It is handled by solving quantum master equations. And Shubhashish will also speak sometime, is Banerjee, and we worked on many of those noise systems and effect of noise, and those tools which we implement in solving quantum information problems actually came from quantum optics and from our old training of solving master equations. So I'll not go in this detail. Okay, so essential quantum mechanics through cartoon. So you should see in the left. So I started few minutes late, and I assuming that I'll talk about 1 hour, so I'm consuming those minutes. So in the left hand side, you see a cartoon that there is a quantum girl, and the boy with the bag with "I love quantum girl" is asking that every time I observe you, I find you in a new look. And the girl is saying that that's quite natural for a quantum girl, because when you observe, I collapse. So every time you make a measurement on a state, say alpha ket 0 plus beta ket 1, so sometime it will collapse to 0, sometime it will collapse to 1. But if you have a state like alpha ket 0, beta ket 1, gamma ket 2, delta ket 3, so it has many possibilities, and it will randomly collapse to one of them. Now in the right-hand side cartoon, a teacher asked a student about a quantum superposition, and the student answered that marmaid. Then the teacher said that, but nobody has seen marmaid. So the student replied that, well, when you do a measurement, it collapses either to fish or to a girl. So this is the incorrect answer. So I told many times in many workshops that the trick for quantum security lies here. How? Because there is a special basis in quantum mechanics. So where the marmaid itself is an element. So if somebody measures in that basis, then the output is deterministic. So you remember what Ashok was telling you about BB84 protocol, that 0, 1 and plus minus state. So when a state is prepared in plus minus and it is measured in plus minus basis, the outcome is same, could be same. So that's the trick that Alice and Bob first compare that in which cases their basis state match. And so they keep only those things and remove rest of the cases. And on those cases, they compare whether their output is matching or not. So by hook and crook, this special basis in which the outcome of Alice and Bob should match must be kept away from the if, and that's what leads to the unconditional security. Now, this is what, if a state is C00 plus C11, the probability of getting it at state 0 is modulo C0 square. And if we talk about photon, then this Ket0 is called Fock state, Ket1 is called single photon state, Ket2 is single. So this is what is Pn, that modulo Cn square. And what I told that if Pn is equal to 0 for any n, then the state is non-classical. So now to understand coherent state, I mentioned that A operating on CNN will give me alpha n CNN, because this is eigenket of coherent state. So multiply from, so you expand this, expanding both sides of the equation, I get alpha C00 plus alpha C11 plus alpha C22, and of course the dot dot dot. Now multiply by, from both sides, I get this kind of equations, and I find out from them a very nice relations that alpha is C0. So this, and again, I do the normalization and I get this. So you can easily see that this is Poissonian, and you will have access to this from YouTube, and you can recalculate this. So this is what coherent state is. So a coherent state is Poissonian. And what is the average photon number? If you take A dagger A, that's called number operator, and you take expectation with respect to D, because A ket alpha is alpha ket alpha. So if you take the inverse relations, so bra alpha A dagger will be alpha star, so you will get mod alpha square. So mod alpha square is the average photon number. So in quantum information, especially in quantum cryptography, I often use a weak coherent source. So weak coherent pulse, or WCP, is a approximate single photon source. So what we do is that we make this average photon number mod alpha square very small by attenuating a laser pulse. So when average is suppose 0.1, then you have hardly any possibility. So this is a cross check that A alpha, A ket alpha is equal to alpha alpha. And this is the property of coherent state is shown by Glauber here. So this is in the heart of quantum optics. So average photon number is shown here. This is shown that it is Poissonian. So what is the property of Poissonian? Delta n square will be an average, and that's shown here easily that you take ket alpha, but you can have a different state and you can choose this, and then you can check that the state is sub-Poissonian or not. So if for a sub-Poissonian state, delta n square shorter than n bar, and that will be non-classical. So this is how most quantum optics people do. But in quantum information, when you are doing cryptography, you are ideally requiring a sub-Poissonian source. And the corresponding sub-Poissonianity and anti-bunching is not exactly same, but they're very close, and we often call that anti-bunching. Anti-bunching is also a manifestation of non-classicality, and that will be required. So I'll skip this. So these are, so you can write for a single mode, if you do solve Dirac equation in second quantization, in our way to second quantization, you can write the field in this way. So derivation is beyond this 1 hour lecture. And then you can introduce these two quadratures, X and Y, which I have earlier written as X1 and X2. And you can check their commutation relations and find out the uncertainty relations, and so which I have done explicitly here, and show this. So from this, you can say that if delta x square is shorter than some value, then we'll call it, it is squeezed in X quadrature and if in at the cost of the other one. So for a coherent state, if you have E1 and E2 into things, that fluctuations looks like a circular form. So in both the quadrature, the fluctuation is same. So in a squeezed state, it happens like this. The fluctuations in reduction of fluctuations in one increases the fluctuation in other direction. And this is employed in LIGO and such thing. And in many of the continuous variable quantum cryptographic scheme. So the whole point which I'm trying to make from the beginning is that quantum optics, traditional tools of quantum optics are still used in quantum information. The way it is used has been changed, and we're coming across new and new applications of quantum optics. So it is more, now often people make comments like quantum optics is losing its charm with the advent of quantum information and everybody is moving towards quantum information. But the message is that there is a very important reason why quantum optics is in the first week of this workshop, because quantum optics is still playing a fundamental role, and it's very interesting, very exciting for, and especially when you handle noise. Noise is the biggest enemy of doing quantum computing. The kind of things you work is you solve actually master equations. There are, of course, certain master equations are solved and you know Krauss operators in certain cases, and you can simply write a matrix multiplications without knowing the background. But if you want to develop a real feeling of how the matter and field interaction is happening, then you need to learn fundamentals of quantum optics. So with this, I will stop and now I can take questions.
Yeah, thank you, Prof. Pathak. So now the session is actually open for the questions. So you can raise your hand, the organizer will allow you. Or you can write in the chat box.
So I'm reading some questions from the chat box. So Devdutt Sharma has written, can we fuse light engineering, nonlinear approach and quantum optics engineering with respect to second quantum?
I have one question. You mentioned something very important about in the beginning of your presentation about slow light. What do you think about in the future about combine PT symmetry and slow light together with the quantum communication? That you think that could be possible?
I cannot follow you properly. Can you repeat?
Yeah. I'll repeat again. You mentioned something important in the beginning on your slides about slow light, right?
Speed lights.
So yeah, slow light. Okay. So what do you think about combine non-emission systems with slow light and also with quantum communication? Do you think that we could be possible that applicate in the future, or maybe not?
Yes, but I mean, immediately I cannot answer you, but I have seen some works means that because the quantum state engineer means the quantum scissors and such state engineering works where the slow light is also used and manipulation is easy, because I don't follow those experiments very directly. Yeah, but I have seen a couple of works.
Okay, thank you.
So Devdutt, I cannot means so what is happening in quantum like nonlinear optics, the traditionally polarization P is proportional to electric field E, and that's very easy to realize. P is equal to epsilon naught chi E. But then only when electric field increases, then you have chi 2 E square plus chi 3 E cube. So nonlinearity is observed only when you have a strong electric field or strong electromagnetic wave. But in quantum optics, and means what the quantum information, we need that nonlinear phenomenon to happen, but still we were working in single photon regime or very weak regime. So traditional classical nonlinear optics will not work here. So the nonlinearity has to be replaced by something. So C0 gate is also a nonlinear operation. And one can easily understand that measurement is non-linear observation. Why? Because quantum measurement, you are working on alpha 0 plus beta 1, you do a measurement and reduce to 0 or get 0 or get 1. So if it was linear, then y is equal to mx. Then for every x there is a y, and every y there is a x. So you can map 1 to 1. But that kind of bijective mapping is not possible between measurement outcome and the input state. So that's why measurement is a nonlinear process, and that can be used to bring nonlinearity in optics. And even when you are working with the weak signal, you can, with certain failure probability, you can do conditional measurements and introduce nonlinearity. So that's the crux of KLM approach also. KLM approach, quantum state engineering, everywhere the nonlinearity is brought by introducing measurement in a tailor-made manner. So is that, and that will be of course used for quantum state engineering and related quantum revolutions, and it's already in use. So someone, Neil Kant, has asked that whether the slides will be shared, because it's already in YouTube, so you have access to the slides in any case.
Oh, no need.
So any other direct questions?
So there's a big stanza from the Subhashish Bari in the chat box. Can you actually?
Okay, Subhashish.
Maybe it's better if I ask directly here.
Yeah.
No, is not non-classical is equal to quantum? No. So everything is quantum. So everything is not non-classical. So non-classical is, so actually quantum information people follow a different notion of non-classicality. So like Bell state, violation of Bell's inequality is non-classical. But there are states which are still quantum states, but they don't violate Bell's inequality. So you can say that violation of Leggett-Gorg inequality is non-classical, Bochen-Speker's inequality is non-classical. So those are notion of non-classicality, that you don't have a classical analog. But there are states like coherent state. See, coherent state is considered to be classical in quantum optics. So does it mean it's a classical state? The answer is no. It's not classical, but it is closest to classical in the sense that it will give you minimum uncertainty. Ideally, in the classical world, there is no uncertainty. But coherent state still will have some kind of uncertainty. So the world is quantum mechanical. But if you have a classical like behavior, or you can have analogous picture in the classical world, then it's called classical. Only when you see, so there are some trick or some criteria in which so you can have states, coherent states, all mixtures of any mixed states which is made up of coherent state is called classical. So quantum and classical are not the same thing. Quantum and non-classical. What was your first question? This was your second question. It feels like the deepest questions of quantum physics are often found in quantum optics. Makes me wonder what is a better proposition, quantum optics as a subset of quantum optics is definitely a subset of quantum physics, and there are many ways to work on quantum physics, and quantum optics is one of the way. And Mark Beck's page is something which I always suggest to students to visit. So Mark Beck explains everything from optics, and you see that quantum optics is as old as quantum mechanics or quantum physics. Quantum physics started with Planck's work. So Planck's work, photoelectric effect, all these are some way related to the foundation of quantum optics also. But of course, there are quantum mechanics contains much more than what quantum optics is. So what is a good way to distinguish a non-Gaussian pure state? And thus,
Anirban, you mentioned about entanglement revival. Can you comment a little bit on that?
no, I did not speak on entanglement revival in this talk.
You know, there was certain death, I think dissipative channel, death and
Yes,
then
yes,
revival.
yes. I mean, those revival were the manifestation of non-Markovian character, means where we have seen the revival, that was non-Markovian channel. So
Okay.
there are two kind of noise, means if for students means Markovian and non-Markovian. So Easiest way to visualize is Markovian channels do not have memory. So if I'm sending something, so this the first pulse has gone. What happens to this has nothing to do with what will happen to the second pulse. That has nothing to do with what will happen to the third pulse. So it's absolutely independent. So that's a Markovian channel. So it has no memory. But in non-Markovian channel, there is a memory part. So it depends on my interaction, the environment's interaction on the first will decide how the interaction of the second will happen. And when it is not Markovian channel, you will always see that there is a continuous decay. But non-Markovian channel, the fidelity may decrease and then again it may increase. So we observe such things as a benefit in the non-Markovian channel, and that's a typical manifestation of non-Markovian.
Thanks.
But entanglements, this means non-classical properties means are. So we have done recently one work with a summer intern, and it was pretty interesting. Means we have restarted Jaynes-Cummins model, and in Jaynes-Cummins model we measured that what is the, say in the beginning the atom was in excited state and I give a coherent state, and then the interaction starts, and whether the non-classicality is conserved or not. So we measure the non-classicality of the atom and non-classicality of the field both using negativity, and then keep on adding, and that beam splitter kind of model, and we find that it's more or less quasi-conserved. It's not exactly conserved, but because the non-classicality measures cannot capture all the non-classicality, but it's somewhat like a quasi-conserved. And in those models, it's very, very clean. That means the non-classicality is dying in something and it's reviving in some other parameters. So Jaynes-Cummins I have never spoke, but Jaynes-Cummins means maybe somebody else has spoken quantum optics. Jaynes-Cummins is a nice model to study. Means if somebody is interested in quantum optics, means this is one of the oldest and simplest thing, but still top journals publishes papers means and on Jaynes-Cummins model.
So
I mentioned many times quantum state engineering means, and this is interesting. There are many interesting terms like quantum Caesar. So normally the coherent state is an infinite dimensional state, and you can apparently, our Hilbert space is infinite dimensional in quantum mechanics, but you can cut the Hilbert space. You can make it 10 dimensional, 20 dimensional, or 100 dimensional, and then it's called finite dimensional. So those are interesting aspects of quantum state engineering, and this can be done, at least theoretically. You can check with a couple of beam splitter, detector, and not mirror, and not difficult to play with. And all such finite dimensional states will definitely be non-classical, because if it is 100 dimension means there is a hole at 101, 102, 103 everywhere, and when there is a hole in photon number distribution, that's non-classical.
So,
Is there any other question?
yeah. So is there any other questions from the audience? So if there is no more questions, let's actually close the session, and let me thank all the speakers once again, and here with actually today's all talks